Welcome everyone back to the Astro Imaging channel and our Sunday night broadcast. Tonight we have a special guest from the Space Telescope Science Institute. Did I get that right? Always kind of trip over that one. Her name is Alyssa Pagan, and she's one of the people that generates those really fine images that we see from the James Webb Telescope. Now I know that we get lots of good science from James Webb, and I think that we all kind of scratch our head and get a headache actually trying to understand it. But what we always understand are the pictures, and I think that we probably digress to those pictures, all of us, and if we want to admit it, that's probably what happened. So Alyssa's going to tell us how that all works and give us a little instruction on how to make those images. But before we go to Alyssa, let me do our routine of sharing a window. Share a window. Well, here we go. Let's take a brief look at our schedule. We got some exciting presentations coming up. We got Alyssa this week. Next week, we got John Hayes. He always gives a great presentation. And he's going to talk about his trials and tribulations of setting up his whole rig down in Chile. The week after this, Sid Fried's going to talk about his slow journey in astrophotography. And after that, Yazo Zhang is he has a nice collaboration. We've seen a lot of his images, and he's going to talk about the collaboration and how they put those images together. Rod Palmier is built an observatory in his backyard and has taken a better part of a year through all the trials and tribulations of that. He's going to talk about it. And we got a couple of pretty full program. Let's see, when's our next? Oh yeah, Sunday, October 8th and Sunday, September 24th. We have open sessions so far. So if people are interested in giving a presentation, want to send us a little note from our site, we'll get in touch with you and see if we can fill that in. So let's stop presenting. Okay, we're back. Now, I have a little introduction for Alyssa. Let me see if I can bring this up. Give me just a moment. Okay, here it is. Well, Alyssa sent me something and I rewrote it a little bit. So Alyssa, please forgive my rewrites, but here goes. Alyssa Pagan is with this Science Visualization Developer. He works on the office, or she works in the Office of Public Outreach with the Space Telescope Science Institute, STScI. She has a BA in Art and Design from Towson University, a bachelor's degree from University of Maryland. She got a nice education. She works closely with the astronomers to create color images of space that are intended to both educate, inspire, and showcase the beauty of our universe. Now, we all know what that means. That means we make these really pretty pictures. And that's enough for us. The amazing visions of the Webb telescope have captivated the world. However, there's a long and involved process for which the scientists' observational data are transformed into the dynamic color imagery. And anyone who's gone to that website, which I'm sure Alyssa is going to discuss, knows that that can be a complicated process. And Alyssa is going to demonstrate live how this is all done. So please take notes. There'll be a short quiz at the end of her presentation. And with that fumbled introduction, I'm going to turn it over to you, Alyssa. Take it away.
All right. Thank you so much, Eric. All right, let's get that going. Well, hey, everyone. Thank you for joining me today. I'm really happy to be here. As Eric mentioned, I'm a science visuals developer, and all that means is that I take data from Webb, from Hubble, other observatories, and make color images that support news releases or science discoveries. And so I'll be talking how we do that today. But before I go too far into that, I think it's kind of nice to reflect on how far we've come, because we have actually the first image anniversary coming up. Webb has been out for like a year and a half. So that's July 12th. There's going to be a new image drop. So be prepared for that on webtelescope.org. But it's just nice to think about just everything that had to go right for us to be able to see these images and the way that Webb was constructed and how we see that kind of construction in the images that we see. And so I'm sure many of you were watching the launch on Christmas Day. I was in my PJs on my couch. I was like freaking out, chomping at the bit. It was just very exciting. And for anyone who did miss it or just wants to see it again, I just have this really cool video showing this launch. Much easier to watch now than it was then.
We're inside a minute now. T-minus 30 seconds and counting. Standing by for terminal count.
À tous de DDO, attention pour les deux comptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And
Allumage
liftoff.
UAP, décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported.
Exciting stuff. So we're done, right? We launched it up into space. We're good. Well, so this is where things get really complicated, if it wasn't already complicated, and that it has to unfold in space. So we know that Webb is a very large telescope. It's a 6.5 meter primary mirror, which has to unfold that's built from 18 different hexagonal segments. And then there's a tennis court sun shield with 5 layers that has to unfold as well. And it has to do all of this while it's traveling to a special point 1 million miles away at L2, or the Lagrange point 2. So that's a lot that's going on. So as you can see here, 178 release devices, 50 deployable structures. Basically, all that means is that there was over 340 points of failure. So if any of those single things went wrong, Webb would not be functioning right now. We would not be getting the image that we see today. And that's just insane to me. So that, again, that includes like unfolding the mirror. So the hexagonal mirror segments, calibrating those mirrors so that we can actually see an image in focus, and calibrating the science instruments. And at the same time as it's traveling to L2, it has to slowly cool. So the camera has to slowly cool because it is an infrared instrument. So that it has to slowly cool so that it doesn't actually create ice, which could be a very big issue. So, but not only did it succeed, but it surpassed our expectations. As we can see, it is fully functional, and we're actually going to get more life out of this telescope than we previously thought. So this is great. And then we get this little near cam alignment selfie. So this was from the near cam pupil image, which actually was a surprise to a lot of people. We didn't know we could actually see this. So this is kind of like a little alignment sanity test. Words are hard today. And so you can see the 18 hexagonal mirrors, and they look good. And the reason why I'm showing this is just this is showcasing why we see the stars that we do, or we see the stars the way they are in the images that we see, and the point spread function that we're very familiar with in these Webb imagery, which creates sort of these 6-pointed large spikes, which is created from the diffraction on each of the hexagonal mirrors. And then, of course, the struts that are holding it creates that horizontal spike. So this is just kind of showcasing why we see those things based off of the instrument. And so this is just a telescope alignment evaluation image, one of the first images that we got that was just a test, and yet we see all these background galaxies, which is amazing. And so we know that Webb is built to do so much science, and so I'd be remiss to not mention the spectroscopy instruments. So there's NIRSpec, there's all these other instruments, NIRCam, which has spectra observing modes, mid-infrared instrument mirroring, NIRISS, fine guidance sensor. All these things are very important, but we're going to be focusing on the image, of course. And particularly, we're going to be focusing on near cam imaging, or the near infrared, just because that has the highest resolution. So, but we will discuss a little bit of the mid-infrared. So why do we care about infrared light, though? Why do we need an infrared telescope? So as you guys know, the electromagnetic spectrum is just tons of different wavelengths of light, and visible light is just a fraction of what we can see. And if we only understood that fraction, we'd be missing so much. We'd be lacking a huge understanding of how the universe works. And also we wouldn't be able to utilize a lot of the technology that we do, like just using our remote controls, microwaves, all that stuff. So we need to expand our understanding and study of all these wavelengths of light in order to understand space better. And this is just a little showing infrared light as the predator sees, why he can see behind sort of a tree in order to find you, and mud cannot save you, as it's even though that's what it shows, that is a myth. So that's just showing the infrared, and something that's more something that we actually use is actually sort of the face technology, the face mapping technology to unlock your phone. So that uses infrared light. So these are kind of like the day-to-day things that we see. But if we're looking at things like in space, here's sort of a parallel of an optical image where we see a opaque bag, and then we see the same image in infrared light, and we can see through the bag. That's exactly what's happening when we're looking at infrared light in space. And so on the left, we have a Hubble image. So that's the visible light image. And we can see this spiral galaxy with sort of these dusty arms. And then an infrared light on the right is actually a mid-infrared image. So it's actually gone beyond the point of seeing through the dust or seeing through that opaque bag. We've gotten to the point where we're actually seeing the dust emitting. So it's sort of the inverse of that visible light image. And then an important reason why we study infrared light is the concept called cosmological redshift. And all that means is that space over time has been expanding, and distant light has to travel through space. And as it travels through space, it also expands. So it gets shifted to the red part of the spectrum. So it gets redshifted. And that is our first galaxies. That's some of our first stars that are forming that we can only detect with infrared light. And of course, this has to be a telescope that's in space, because a lot of the infrared light gets absorbed by our atmosphere, and like other space telescopes. And of course, the seeing is just so much better in space to begin with. So that's just an added benefit. And of course, Webb is not a replacement to Hubble or any other telescope. It's meant to work in tandem with Hubble, just like we use different medical imaging to see different parts of our body, understand different parts of our body, like our, x-rays to see our bones, and, MRIs to see, our soft tissue. And so everything works together to get us a full understanding of how things work, including space. And so this is just a first look. Well, not really a first look now, I feel like, with all these things coming out, but some of the images that we've seen that sort of characterize our universe and actually helped us understand a little bit more about our universe. So this is the Pandora's cluster. So we're starting out like very early universe. So this is a deep field image. It has 3 clusters that are going to form into a supercluster. And so this also has some gravitational lensing. So what's great about this image is that you're seeing really, really redshifted galaxies, so very distant galaxies. And then on top of that, because of the gravitational lensing, you actually get to see an even more magnified view. So you get to see things that are even more distant than that the telescope is capable of. And there's over 50,000 sources in here. So it's just insane. And this is like a small field of view, but you're seeing so much in that little patch of sky. And that's all because of the sensitivity of the Webb Space Telescope. And this is just a diagram showing that bending of light because of that huge mass of the cluster. So you can see something much farther away just because of that magnification. And then we're coming a little bit closer in. So now we're dealing with galaxies. So Webb's looking at galaxies. This is Stephan's quintet. So this is actually technically a quartet. It's a little bit of a misnomer because all these galaxies in the cluster are actually 290 million light years away, but this foreground galaxy is much closer to us. So that one's about 40 million light years away. And you can kind of tell by the resolution of it. But this is actually 3 different wavelengths of light that we're kind of seeing it in. Well, the third on the right is actually a combination. But on the far left, we have the Hubble image. So that's the visible light image. So again, something that we're very familiar with. We see the dusty spiral arms. We see sort of the young stars that are blue in the spiral galaxy. And then in the middle image, that's the near infrared image, so the near cam image. So those dust, we see through the dust. The dust in these spiral arms, they just disappear. We see right through them. And because we're looking at an infrared image using Webb, we just see all these faint background galaxies just pop into view. So inevitably, any sort of image with Webb becomes a deep field, which is crazy. You're going to find a ton of galaxies that you might be the first one seeing. So it's pretty crazy. And then on the right, we have a combined mid-infrared and the near-infrared. So you can see through the gas at the same time. With the mid-infrared we've applied, you actually see the gas emanating or the dust emanating. So it kind of gives you this full understanding of what's happening. And then you also get to see sort of how the merging, oops, sorry guys, I did not mean to do that. I did not mean to unshare. So I just wanted to get rid of that. Okay. So yes, this is just showcasing how the merging and interactions of these galaxies are influencing sort of the evolution of them. So it's just very important to understand these different stages of this so that we can understand our own galaxy. Okay, now we're moving closer still, and this is a star-forming region. This is something that you guys are probably very familiar with. This is the Pillars of Creation, or a section of the Eagle Nebula, and this is actually a combined view of the mid-infrared and the near-infrared. So again, we're kind of getting two worlds where we're seeing through the gas, we're seeing all these stars popping out, like you're seeing these red stars that are young stars embedded in this dust. And then at the same time, you are actually seeing some of the dust emitting sort of in the background too. So we're getting a really good understanding of sort of the evolution of stars in this case. And now looking at, that was more of the, the beginning stages of a star. This is the death of a star. So this is the supernova remnant Cassiopeia A, and this is one of the youngest explosions that we know of. It's 340 years old. And again, this helps us fill in the gaps between, star death, star evolution, star birth. And you can see sort of the dust emitting in red, impacting sort of the rest of the interstellar medium. And then you actually have sort of the white pinks being heavy elements that are emitting. And again, closer, we got exoplanets, which Webb can detect with such crispness, such precision, and that it's able to get these beautiful transit light curves. So when a planet transits over a star, you get this little dip in the light, and then Webb is able to look at that with spectra and break it down into component colors of light to get sort of like a barcode or signatures of certain elements or the composition. And Webb does that so well. It produces very, very crisp transit light curves, which is something that we're not going to really talk about because it's not really imaging related, but still very cool stuff. And then this is more of the direct imaging part, which is also very cool. That Webb has the sensitivity to be able to detect exoplanet that is 10 times fainter than its host star in this case. So the fact that it has the power to do that, I think, is just blows my mind. And the fact that we'll be able to detect or directly image a lot more exoplanets is also very exciting. And now we're in our solar system. So this is an unprecedented look of Uranus. We can see the rings very clearly, and it's the best view since Voyager of the rings. And of course, something that we're also not used to with the solar system images of these objects is these background galaxies again, just like photobombing every image, but not in a bad way, of course. It's something that we really enjoy. Okay, so now we're getting to why do we make these color images? I feel like I don't need to really explain myself here with you guys, but just to give you an idea of sort of what we're thinking about when we make these images is from an outreach perspective, at least, is we want to visualize the data because numerical information is very important for science and research, but when it comes to actually like showcasing the bigger picture, seeing the data all at once, you want to see it and you want to see all the filters at once. And then of course you want to illustrate these scientific discoveries and concepts to everyone, not just those who have a certain scientific literacy. We want to make it understandable. We want to disseminate it. We want to make a bridge. And that sort of goes into engaging the public, making people interested in science, wanting to learn more about astronomy and get more of like, and bridge that gap essentially. Okay, so talked a lot about these images, but how do we even get to the data? So you guys may or may not be familiar with this, but all the data is actually public. At least it becomes public after a 6-month proprietary period. But it all becomes available at least at some point, and you can find it at the Mikulski Archive for Space Telescopes, and this is hosted by STScI. And so all the data comes here, the raw and the calibrated data. And when it comes to MAST, you'll find that it's gone through a calibration pipeline already. And so you can get all the raw data yourself if you want, and then you can run it through the pipelines at certain steps if you want to not use the default parameters. But the default parameters in this case usually is good, and it can be pretty tedious. For Hubble, of course, the pipeline has been refined because it's, a long observatory. It's been around for a long time. Webb is still getting, the pipeline is still being refined. So there are things that you can do better. But for now, the calibration is very good from the archive itself. Okay, so how do we actually find things in the archive? Because it can get a little convoluted and crazy. So the easiest way to do it is if you see an object on like webtelescope.org, which is one of the places where we put official news releases of Webb imagery, is that under that image, you can see a section called the fast facts, and it will give you, the object name, it will give you the coordinates, which is really important. And one thing that's really, really easy or overlooked is this proposal or this data description right here. And if you use that, it actually takes you directly to the data. Now, of course, this is only if you see something at webtelescope.org. Maybe you saw something else, or you're just interested in something like that. You just need to know the coordinates, and then you can filter it down a little bit further. So we can go back to the Mikulski archive, and I'm just doing a search for the Pillars of Creation or the Eagle Nebula, but I'm using the catalog name. So I am putting that right here in the object name. You'll want to do an advanced search. That's just the easiest way to get what you want and, get a little bit refined. And then you want to do the mission. And so since Webb is a very new mission, you're not going to get a whole lot of data. So it's a great way to sort of refine the search. If you're dealing with Hubble data, you're probably going to have to put a little bit more information to get your queries down. So you'd want to put JWST and M16, and that's good enough. And then you get to this page here where you can refine it even further if you want to, like by instrument, by the scientist, by filter, any of those things. It's really nice on the right. You have a little sky view here where you see the footprint of the NIRCam instrument. In this case, it's the mosaic of the NIRCam of this Eagle Nebula. And so we only care about the NIRCam specifically for this example. So that's what I've selected. There's 6 different filters here. And actually one of them, it looks like it's a duplicate filter, this 4.4 micron filter. So that's what you care about the most, is these filter names. It gets a little weird because the names of these filters don't really change depending on what instrument, or I should say what observatory you're looking at. But you can know that for Webb, when you're looking at this like 444, that's the filter name, and that means it's 4.44 microns. So just in case you wanted to know. And so again, this 4.4 micron filter is actually not a duplicate. It's just the way that the telescope works. There's 2 filter wheels, and so one goes through the other. So the narrow band can go through the wider band filter. So there's actually a narrow band filter, the 470, I believe, going through there. So you want to select all of those, and then you want to download them. So as you can see here, it's the 470 narrowband filter that I was talking about. That's within that 4.4 micron filter. And so here I've selected minimum recommended products, and that gets you all the calibrated files. So that gets you your 2D bits files, the ones that your image, what you want, what you care about. Now, let's say you wanted to reprocess the data because you wanted to play with the pipeline. You can totally do that. You'd have to unclick this, but it's a lot. I'm going to warn you, it's a lot of data. And it's pretty large. And this data alone, the minimum recommended products, is a lot of data too. It's about, for the mosaic, it's about 5 gigabytes for the short wavelength filters. And we'll get to that in a little bit. It also contains extra files besides the 2D. So it says the i2D fits file. That's what you want. That's your image. But when you open this up, it actually has some extensions that just had some byproducts from the calibration pipeline, like masks and things that you don't need, just to let you know. Okay, this is just like an overview of the pipeline, just very brief overview of the data going through stage 1. All of the data goes through stage 1. And then it gets split into 2 different observing modes. So you have the image and you have the spectra, and then it goes down even further still where it gets the full stage 3, completely calibrated, and then it goes into the archive along with the raw data. And now before we even get to the point of getting this data, which is something you guys are probably more familiar than even I am familiar with, is that having to plan getting these observations. So we have to plan way ahead of time for these outreach images or anniversary images to make sure that we, first of all, the observatory can see it on the sky. We have to think of the filters that best will capture this object and the science of this object. And we actually have to think about sort of how many orbits we need in terms of like how many tiles we need and all the things like that. So dither patterns, all that good stuff has to be considered way ahead of time before we even, put in the proposal. So it was a little bit of a reveal, but maybe not. That is actually the Carina Nebula, but it was in an inverted black and white image, very small section of the Carina Nebula. And what I'm highlighting right here is actually one tile from this larger mosaic. So there's a lot that goes into these images coming together and becoming calibrated. And that is, first, the raw data goes through the pipeline. So this, again, is just a quick overview of the pipeline, just in case you're curious and you want to mess around or you're just interested in general. Now, infrared cameras don't work like CCDs in the sense that they can read the electrons without destroying them. So that's really nice because you can do lots of different measurements, and so you can prevent saturation. There still can be saturation in the initial sort of frame, but it does really help with that. So this is just the signal that's building up in this stage 0. So this is your raw data signal building up, and this is the stage 1 of the calibration. So this is when your ramps are fitted. This is where you are subtracting your bias, subtracting your darks, and you're flagging things like cosmic rays, dead pixels, and saturated areas too. So this is where you're kind of forming masks of these pixels. And then next, that's when you calibrate your image further. So this is where you're applying the flat field, you're doing distortion correction, you're putting in your wide world coordinate system and things like that. So now you're getting very close, and to the very end, this is your final exposure where you fully calibrated all the data for multiple exposures, and at the same time you can combine all these different exposures to create a mosaic. So all those things are happening at once. And you can see that there's still those black things in the middle of the stars, as we know, that we were discussing before. And we will get rid of that. Unfortunately, the pipeline puts that there because that is where it was saturated. So we can't go back because the first frame was saturated, if you saw. Okay, so again, that makes one tile of this full mosaic. So it's a huge process that was happening. All right, so it looks like the screen went blank, but it actually didn't. So I was showing you sort of a stretched image of the Carina Nebula. This is how the image looks in one filter when I bring it in to my computer before I've done anything to it. So that's just a sort of sneak peek of that. So this is the basics that I'm sure many of you are familiar with. I'll start with like a basic overview using the Carina Nebula, and then I'll kind of get a little bit more detailed with some techniques specifically that I use for the pillars of creation. So we'll start with, yes.
Can I ask you a question?
Of course.
When you in the Mikulski archive, I don't think you showed exactly how you download the data.
Oh, I can go back. Yes, I don't think I did that. So sorry about that. Okay. Okay, so if you click on whatever you want, there's actually a download button right here, download to your basket. That's what you want to hit where my cursor is. And then after it gets into your download basket, then you can actually hit the download button and it will put it in a zip file. And then from there, you can open it up in sort of FITS Liberator or any other software that can liberate the FITS, which we'll get into in a little bit. So hopefully that answered that.
Thank you.
Mm-hmm. All right. All right. Slides. Okay, so back to the image stretching. So this is something that I'm sure many of you astrophotographers are very familiar with. We have to do it with all of the space observatories as well. This is actually an example of bringing one of the filters or one of the images into DS9, which is just a visualization software. I don't work in this in terms of photo editing. It's just something to really quickly get an idea of what's happening, and you can just get some information really quickly. And this is actually showing the deep field image in the 2.77 micron filter, and it looks black, but we know there's a ton of information there. It's just these instruments are so sensitive to light that we have such a high dynamic range, and we have to compress it so we can actually see what's happening on our screens. So you can see all that information is just sort of, or we can say our histogram distribution is just on the left side, and we want to stretch it out. And so that's what we'll be doing. And so these are just showing different stretches. The first on the left, which is a simple image of a pair, it's just 4 different values here: black, dark gray, light gray, and white. And then so the first one is just us doing nothing, 1-to-1 linear. And then this is a linear stretch, and you can see we are bringing up sort of the brighter areas, but we're completely clipping them. So we completely lose them, which is a no-no. We don't want to do that. So this is an example on the far right is what we call a nonlinear stretch. And that's exactly what we want to do with our astronomy data, because we're bringing out the brightest regions and bringing out the darker regions, but we're not losing any information. And so this is an example of the same image of the deep field, this max, in the 2.7 micron filter, where we have stretched the image, a linear stretch, but you can see where we've clipped the white. And we don't want that because we lost all that information in sort of the brightest regions. So that's a no-no. So that's why we do the nonlinear stretch here. And we can see, oh, we can see all the details in the brightest areas. We can reveal all those faint details in the darker areas. And that's the balance here. And that's really always the balance with the stretch, is bringing out those details, but also suppressing the noise. So it's always a little bit of a balance here. And this is just a FITS Liberator. So this is something that we use very often. We use PixelClip as well, but this is completely free. So just in case you've never used it before, here is a link to it. And I'm happy to share these slides with anybody to get to it, where you can download it for free and use it for free to liberate any of your fits and then export them as TIFF files. And that's what I'm doing here. I'm applying the stretch to bring out all these faint details in this image, and then I can save it as a 16-bit TIFF. So, and I have to do that with all of the images though. So all the different filters that make up the Carina Nebula. In this case, we have 6 different filters. So these are all how they look linear. So straight when I bring them into sort of a FITS Liberator or a visualization program. And this is after I've stretched them. So bringing out all those details again. So we've done that, and now we can focus on chromatic color. So it gets a little weird because we're talking about infrared light, but essentially it's the same as visible light. And so this is just a video of the mid-infrared instrument, the MIRI instrument, showing the light going through this instrument, and it's being redirected throughout onto this filter wheel, which collects specific wavelengths of light. And then once it goes through that filter wheel, then it gets redirected to the camera. And so we have an image, and those specific wavelengths of light have specific colors associated with them, at least in the visible light. But we can do the same thing. So basically, shorter wavelengths in visible light are bluer, and longer wavelengths light are redder. And so we use that same relationship and we apply that to the infrared part of the spectrum, or essentially we are shifting that relationship into the infrared part of the spectrum, just like that, so that the shorter wavelengths in the infrared are the bluer colors, and then the longer wave infrared are the redder colors. So we keep that relationship and apply it here. So that's what we call chromatic ordering. And so in this case, we have the 0.9 micron filter. That gets your bluer color. We work our way up. So 2 microns green, 3.3 microns orange, et cetera, moving along. Now, we do see an outlier here on the far right, the 4.7 micron filter. It's yellow, but we're not exactly breaking the rules too much here. And the reason why is that the 4.4 micron filter is actually a very wide filter. So it encompasses the 4.7. And additionally, we see this feature, which is hydrogen emission, very hot hydrogen gas. We see this feature also in the 2.12 micron filter. So it's not really changing this sort of rule that much. And the reason why we want to do this is because This is a very important feature. This is showcasing these young stars and their jets underneath that are embedded in this dust. And we want to make sure we showcase that. And if we just made it red, it would get completely lost in that wider 4.4 micron filter. So we have to make these choices to make things clearer and also beautiful. And so before we create the full color image and additively combine them together, we do have to correct some artifacts. So there are things called 1/f noise. So it's the striations here that you see, this banding, which happens more when the shorter wavelength channels. And then we also have these star cores that are black. And again, that happened because of the pipeline. And so we do have to get rid of those. And we'll go a little bit into how we do that in another example. But that's something we do have to deal with on a filter by filter level. So this is the initial color combination of the Carina Nebula. And this is where it becomes a little bit more like photography work after you've color balanced it and white balanced it. It gets a little bit tricky though, because we don't have a dark, or we don't have a background sky that we can neutralize, which is something that we usually use as an aid to make it neutral. But we can use the star cores as sort of our white reference. But of course, we'd had to replace those before. But again, there is no clear point where it becomes transitions from objective to subjective. We're kind of weighing all those things at the same time. But we do think about specific aesthetic principles, like, you know, the clarity in terms of like the details, and also clarity in sort of the message and the science, as well as color and composition. All those things that really help showcase what's actually happening here. And for example, we have the Carina Nebula here, and you've seen it mainly in this orientation, though technically, oops, I went backwards. But technically north up is actually this orientation on the right. But that doesn't seem quite right, because first of all, we'd have to crop in and we lose a lot of real estate, which is a no-no because all that data is super precious. But also, it doesn't really convey what's actually happening here. And it kind of feels like it's just off balance, doesn't feel natural. And so we rotate it in this horizontal way because it actually acts as a context for what's actually happening here. Just like these are like mountains and a sky. So like in the real world, mountains get eroded by sort of weathering. This is the same thing is essentially happening here, where these mountains of dust are being eroded by these hot stars. So that sort of connection really helps tell this story and also makes it more familiar. And so again, not a clear point where it becomes subjective versus objective, but again, we're looking at it with sort of an eye of a photographer, and we really want to bring out these different features. I'm also working closely with scientists at this point, so we're making sure that we are showcasing the science that they want to see. And so right here, I did like a little shift, so the relationship between all the different filters is the same. I'm just shifting a little bit to the bluer end, because this feels a bit more natural to me, because it's more like an orange dune sort of feeling and like a dark blue sky, a little bit easier to sort of digest. And then this is a case where I feel like in an attempt to really bring out those details, I've gone too far, and it's become something that's is not really representative of what's actually happening here. And that happens a lot. I think you just have to pull back. And at this point, again, I'm talking with the scientists, and so this like gas here, it's there, it's really there, but it's sort of obscuring the 3D nature of the dust, and they really wanted to see more of the structure. So I ended up doing a lot of pulling out the local contrast in this mountainous region to really bring that out. And the color separation really helps showcase the difference between these two different phenomena. So the dust is like this dense cloud, and then on top we have ionized gas. So it's really like contrasting those two different things that are happening here. And so this is the final image where everything just sort of comes together, just, you know, feeling more natural. And that seems kind of objective to say, but that's the best way that I can describe it. So let's look a little bit more in depth here. Hopefully I'm not running. Okay, good. And this actually has a very similar color palette to the Carina Nebula, and that's because it's actually a similar object. It's a star-forming region, and it has the same filters, so it makes sense that it would actually look very similar. And so everything that the other Carina Nebula is telling you is the same in sort of the star-forming region in the pillars of creation here. So just going to start again with the stretching. So on the left, again, is how we start out, straight from the calibrated data. And then in the middle, we have a stretched image. And on the right, we have a nice sort of cleaned up image where we removed sort of the artifacts and, you know, those black star cores here. And we use a script called PixelClip, which was adapted by Joseph T. Pasquale, my counterpart from Garrett Barari. And I'm happy to share that. Basically, what it does is that you select sort of this point, this dark point, and then anything below that gets replaced with the brightest point in the image, depending on how you change the script, or the nearest neighbor. We usually use the nearest neighbor because that tends to work the best. And it's not perfect, but once you've combined all your filters together, it ends up canceling out, and you pretty much get a nice sort of white core. And that's what we're aiming for here. Okay, and so the next thing is that there's actually two different wavelength channels. There's a short wavelength channel and there's a long wavelength channel. So everything that's 2 microns and below would fall in the short wavelength channel, and everything that is 2.7 microns and above falls into the long wavelength channel. And I'm mentioning this because they're actually different sizes. So you actually get more resolution in the short wavelength channel because it's constructed with more chips than the long wavelength channel. So you actually have to align these images together. Now, luckily, the alignment is really taken care of in the pipeline process by default. You might have to do a little bit of tweaking as long as you rescale the images by a factor of 2. So if you rescale the images by a factor of 2, or you can actually reduce one of them by a factor of 2. Either way, it kind of depends on how much RAM you have. So we tend to keep the highest resolution as possible because we want to, you know, pull out it as much as we can. So in this case, the 4.4 micron filter, we have to scale it up by a factor of 2 to get to align with the 2 micron filter. Okay, and so banding is a big thing with Webb. I'm sure if you guys have played with it a little bit, you'll see it. And there's a lot of tools out there that you can work with if you're a Windows user. There's actually a banding correction tool in GIMP. I haven't messed with it too much, I can say. But there is actually an astronomy tool action that I really like. It actually comes in this package, which I listed right here. I believe it's like 25 bucks, but I think it's well worth it. I use a lot of the actions in there. Not like they might not work completely, but in conjunction with some other tools, it helps very, very much. And in the case of web imagery, the banding, sometimes you'll have to resize the image in order to correct the banding. So for instance, like with the mosaic, like pillars of creation, if you want to reduce that banding, maybe that algorithm won't work on the full-size mosaic. But if you scale it down, make a difference image, scale it back up, and subtract that from the main image, so you're still preserving the resolution, you can it can work better. So that's just one sort of like technique that we use a lot to help reduce those bandings. That's mainly in the short wavelength filter. And so this is just an initial color composite of those stretched images. Same filters as the Carina Nebula here. And there's no one way to do this. Sometimes I use a different sort of procedure depending on the image. And I'm sure all of you have a different sort of procedure that works for you or process. My counterpart tends to work in PixInsight first. Sometimes I do that as well. But I tend to, at least in the ending stages, spend a lot of time in Photoshop. Any photo editing software will work, including Photoshop, GIMP, anything that sort of you're interested in. This is just like a little example of my file and how I'm arranging my layers, and lots of curves adjustments and, you know, things that I'm sure you're all familiar with. And so again, this is just a step where I'm improving the color separation and the contrast because I'm trying to emphasize the details in these different and the features in these filters, because that's what's really important. These different filters are telling us different elements and molecules that are in here, and also the difference between sort of the dust areas in the sky and the gas. And one tool that I find really helpful in particular for web image, which is like have so many stars in them, is that actually the good old Russell Croman made this star exterminator. And so I can use this not to get rid of the stars permanently, but to remove them, create a layer of them so I can work on them separately from the actual image. Or I can also help you to reduce the stars size if it's just like too much that's taking away from the rest of the structure of the image. So that's just like a little example here. I believe that's the Cygnus loop, actually. And so this is an example of me extracting those stars from the pillars of creation. It's very hard to see, I'm sure, on this presentation, but there are chips where there has been dithering. There's seams you can see here that you can't really work on if the stars are in the way, because you inevitably might remove a star, or you might add a star. You don't want to do that. You don't want to introduce artifacts. So it's just like a nice way to kind of separate the two and also bring out the features in the structure and bring out the depth without saturating the stars, which are already too bright to begin with. So it's just a kind of nice way to really see things clearly. And then, of course, we have things like cosmic rays, which is not a huge deal in the web, interestingly enough, because of the pipeline and the way that the infrared pipeline works. You don't get a ton of them, but there's still a lot of them. And that's sort of like a nice, very discrete clone tool, should I say, but really you're just sampling the background sky and you're not adding any data. You're doing this very sort of modestly, I should say. Okay, so I've talked a lot about star forming regions, but there's not a one size fits all, which I'm sure you guys have all found. Different objects require different treatments. And so these are just a couple of them that I'm going over through really quickly. For instance, the Tarantula Nebula is interesting because we had 6 filters, but we ended up only using 4 filters. There's a reason for that, because sometimes more filters is not better. Sometimes more filters creates confusion aesthetically or scientifically, and it can get muddy. It can get distracting. And so sometimes in order to bring out features, you actually have to be very selective about the filters you choose. And also, we did something called continuum subtraction. So there is a feature called polycyclic aromatic hydrocarbons, which you see in the 3.35 micron filter. And you get that, well, first of all, it's a more narrow filter than these wider band filters. So it's showing something more specific light. And so what you want to do is you can create this continuum subtractive filter. Basically, you're trying to subtract the contaminated light. So anything that spills into this filter that you don't want, you can subtract the nearest wide filter above or below. So in this case, we're subtracting the 2 micron filter from the 3.35 micron filter to get us our pause, so to speak. And that's just a fancy word for soot, essentially, but it's very important to astronomers. And that also adds a lot to the how dynamic this image is. And so let's just take a look really quick of this image of the Tarantula Nebula without this filter, without these polycyclic aromatic hydrocarbons. And this is sort of our initial color composite. And then this is us calibrating the image a little bit, color balancing the image, I should say, and doing sort of that photographer, aesthetic eye work. And then we'll actually bring in that filter. So that was the pause right there that you just saw come in. And it just really makes those come to life. It really pumps it up. It really differentiates what's happening here, gives it a little bit more depth, makes it a little bit less flat. And now you can see that if we just added that in there without doing the continued subtraction, it would kind of get lost and get a little bit muddy. So these are the things that you kind of have to think about in order to make something aesthetically pleasing, but also scientifically clear. And so that's just a little compass image of our Tarantula Nebula here. And I've been talking a lot about the NearCam, but I would be remiss not to mention the MIRI. It's got wonderful data. It's just unique. It's very different. It's a very different way of looking at things. And so the way that you treat it can be a little bit different than the NearCam. But what's really nice about the mid-infrared is everything's the same in terms of chromatic ordering, how we approach it. But the filter sizes, or I should say the file sizes, are very small in comparison. So if you just want to like start out and play with it without having this huge investment of like these large size files, MIRI is a very good place to start. So highly recommend that. Okay, and then for deep field images, we have like a little bit of a different approach in that we usually stack the closest filters together to form sort of our blue, green, and red color channels. And the reason for that is because these deep fields, they are showing us very important things with the color. So the color actually represents the distances of these objects. So we really want to increase that color separation. And by stacking those together, we can do that. So this is the SMACS deep field image again. And you can see that the whitish, bluish things are the closest things to you, like the foreground stars. And the smaller, really red things are farther from you. So those are the most distant things, or they're very dusty. So it's really key to have that sort of color coding, so to speak. And now if we're talking about planetary objects, there's a lot that we have to do here because we have this wide field image, which is pointing out these really far away galaxies. That requires a different stretch than the planet itself, the disk, and the rings. So the rings are kind of faint compared to the planet and its planet's disk, and then the deep field or the galaxies are even fainter still. So it requires like 3 different stretches that you have to put together in order to see everything. So it's like HDR like to the max, but you kind of like force it to happen. And it's because you want to enjoy and see all the features at once, or else you're just going to get a blown out image in the disk, or vice versa. You're not going to see anything in the background. So that's just something that you want to do. And this is a very simple example, nothing really new here. But the reason why I bring it up is because we like to follow chromatic order, and it looks like, again, we have like a little bit of an outlier here of the 4.7 narrowband. Again, the 4.4 micron filter is very wide, so it does contain that. But you can make decisions like these because, as you can see, this orange stands out a lot better against the red than vice versa. So you have to make decisions like these to showcase those gas, that structure that's really interesting in here. So aesthetically and scientifically.
Alyssa, can I jump in and ask you a question real quickly?
Yes, absolutely.
John actually posed a question, do the colors represent temperature or chemical composition? I think maybe what he's really asking is, how are you assigning color? How are you choosing color? And what do the different colors represent? So maybe you can kind of explain the different filters and where that's coming from a little bit.
Right. No, it's a bit complicated because we are dealing with infrared. So it's not direct relationship like one-to-one like Hubble is. Like for Hubble, if we have a hydrogen filter or like H alpha, we know that's going to be like a magenta, and we can assign it such because that's what we see. Now, in the case of infrared, it's more of us taking that same relationship and stretching it down. It's like if things were redshifted, and then we're trying to unshift it, so to speak. So we're keeping that shorter wavelength filter that may have been, it's hard to think of like an actual element, but we're taking that shorter wavelength filter in the near infrared, and then we're just going to apply it or shift it to the visible part of the spectrum. So we're basically taking all those filters in conjunction and then shifting them down and then assigning it in that way in their relationship to each other. So hopefully that makes a little bit of sense. And the reason why we do this is, well, first of all, you want to be able to appreciate these images. So everything in infrared inevitably is sort of like what we call a representative color image. But it really has to do more with temperature, I think, is sort of one of your questions, is because the shorter wavelength or the like higher energy is going to be the bluer color, and then the longer wavelength or the lower energy is going to be the redder color. So that it's going to do a little bit about temperature, and it will also have a little bit to do with elements. In the case of sort of these imagery, the hydrogen does tend to be red as well, but it really depends on the images and the filters you have. Because to make a full color image, you can't necessarily assign all the filters exactly the same. It really depends on the collection of filters you have to begin with. So hopefully that makes sense.
Perfectly. And Eli actually just hopped in with one, and I'm not sure I even understand it, so I'm just going to read it. He said, are the polycyclic aromatic hydrocarbons mentioned formed in the nebula? And if so, are the structures and mechanisms of formation known?
So as far as I know, it is formed in the nebula. And honestly, I don't know much more than that. They tried to explain it to me, and the best thing they could say is like soot. So it's kind of like volcanic ash. And I think that's basically all that I know.
Okay, great. Thank you.
Mhm.
Alyssa, one more thing. You mentioned a script to get rid of those black centers in the star. Could you post a link for us that we could put in the chat?
Yes, absolutely. I don't have that link yet, but if I email it to you guys, would you be able to share the link?
Yes.
Yeah, we can put it in the video description. Yeah.
Okay, great. I can definitely do that. All right. So I've been talking a lot about these outreach images that we produced, but a lot of the work that we do is actually on imagery that was intended for science. So basically all that means is that it wasn't this perfect observation to make it look beautiful. It was just to get the best science. And that does not always make the most beautiful image. But that's where the real fun comes in, because we have images like this, which is NGC 346, I believe, which is in the small Magellanic Cloud. And you can see there's chip gaps. So there wasn't dithering to fill in the gaps. They're just trying to look at certain stars. And then there's also some regions where there's very clean, very high signal. We have got other regions with very low signal. So there's tons of noise. So there's a lot of having to play around with this, using the longer wavelength filters to fill in sort of the chip gaps and other things in order to bring this image to life, essentially. So this is the step after I've done a lot of the process that I talked about, like reducing the banding and then just doing things to kind of reduce the noise, and then just make everything feel a little bit more uniform, because we don't want it to seem like something is very crisp and clean and then something else is just kind of mucky. So this is just an image of NGC 346 before I've done the cleaning on the separate filters. So if you just combine them sort of raw, just like that, so you can see the areas where there's a lot more noise or a lot more signal versus other areas. You can see the chip gaps, you can see the striations. It's kind of a little bit of a mess, but it's kind of like a fun sort of like puzzle that you have to solve. And so this is after everything has been cleaned and we're starting to color balance the image. And so this is where the color separation is very important, because we're showcasing two different types of hydrogen here. We have the molecular hydrogen, which you see, which is kind of this knotty bits, very dense bits. And then we have this ionized hydrogen, which is these gassy red bits. And then, so it just really helps really distinguish the star forming region and the regions of where the star forming is actually happening and where these stars are sort of heating up this dust and then there's gas emitting. So this is just an example of just one of the images where you just find in the archive, and it will be kind of hard to kind of piece together, but it's just, you know, it's really fun and there's no one way to do anything. I just want to like make sure that that's clear for everyone if you just want to take a stab at it. But yeah, I think that's all I have. So if there's any other questions, I'm happy to answer the best that I can.
I think we've hit them all. The only question left out there that we didn't answer is, you know, just how did JWST take the what Isaacs calls the near cam alignment selfie?
Oh
And
God.
so maybe you could talk about that just a little bit.
Yes, I still don't quite understand. My counterpart actually made a blog that I'm happy to share, and he like did a lot more research into it. So it's like a pupil mirror that somehow is able to bend the light in such a way where it can see, but it's actually in the near cam instrument. So how it exactly does that and how it reflects or refracts the light in such a way, I'm not quite sure. But I'm happy to share that blog link when I share my script with everyone. It's very interesting though.
That's great. Yeah, we'll put that in the chat as well.
Mm-hmm.
Alyssa, you can stop sharing if you like.
Oh, yes.
You got more things to present.
Nope.
I've got a question for you, Alyssa.
Yes.
How does somebody get a job like yours?
Okay, so I have to say it's a lot of luck. Being at the right place at the right time, and also just having like a specific background that just kind of set me up for success in that way. I was pretty lucky in that. I just ended up doing something that I really was interested in. So I liked art, so I studied art. I liked astronomy, so I studied astronomy. And I didn't really realize how the two could come together until actually observational astronomy. And I'm like, oh, you know, these images don't just exist of like the Hubble imagery, like someone actually has to go in there and like, you know, reduce the data or, you know, remove the artifacts and make a color image. So it is a little bit about luck and also about bothering STScI for a while. I stalked them for quite a bit of time until this position came to be. And basically it was just like, hey, we're looking for someone who has a little bit of art and science. And I'm like, please take me.
Joe had been looking for someone for quite a while, as I remember it.
Yes. He says I'm a unicorn, but that's what he said.
Unicorn. Do you get involved in any of the pre-processing?
Not a ton. Every now and again, we'll have some data that the scientists haven't been able to really process or get to a stage that's clean enough for us to work with, and we'll have to go in there and kind of throw it through the pipeline, which is not, I would say we're not like experts at that yet, because the pipeline is still pretty, I wouldn't say it's clunky. It's just, it's great at what it does. It's a very large Python code, and it can be a little bit tedious to kind of go through the different stages and get exactly what you want out of it. So it just takes a little bit of time, but it is actually very interesting and very powerful, and it will always constantly being refined. It's on like GitHub, so anyone can actually go on there and actually see it. And there's all this documentation about it also available for anyone who's far better at coding than I am. Take a look at that.
Anyone that wants to abuse themselves and get frustrated.
Yeah.
So the only one I can think that would do that would be Tim.
Yeah.
Because that's what he does.
Alyssa, we do have a couple other questions popping in. Building Rainbows asks
Great.
if you would, if you could discuss how you might approach merging Hubble data with Webb data.
Yeah, that's a great question. And honestly, that also depends on sort of what we're trying to convey. Sometimes we take Hubble data and we'll just use one filter, and that could be just like a short wavelength filter. If we're just doing like visible and infrared, or if we're doing X-ray and Hubble and infrared, maybe, the short wavelength filter will be the Chandra data, and that might be the purple. We'll, use purple for that, or for Hubble, we'll use maybe green, or etc. So it kind of depends. Sometimes it will be singular, like monochromatic for each sort of data set to make it less confusing for people. Because sometimes if you make a color image in one, instrument or for one observatory, and then you stack that on top of another image, it kind of gets lost and you're not sure what is what. So we try to make it as clear as possible. So sometimes that means combining two filters together. So maybe like for Chandra, it might be purple and blue, and that will be sort of the low and high energy wavelength X-rays. And then for Hubble, maybe that will be green and orange, and then maybe Spitzer in red.
So your color mapping can get a little bit crowded sometimes.
Yeah. So it's really, it can be tricky because, you definitely don't want to create color confusion. And sometimes, creating something that's aesthetic, but also not confusing, that can kind of be at odds with each other. So it really is sort of a case-by-case basis.
And
Great.
do you ever have to fill in, I'm sorry, Tim, you ever have to fill in data that you might be missing from one source or another with say Hubble data or Webb data?
Sometimes we'll do that. Sometimes often, well, not often, I would say. We generally don't do that for like a press release imagery, or I should say like an anniversary image, just because that's like meant to be sort of like a pristine, just completely exclusive to that observatory. But like for maybe like a science release, there are times where we will want to showcase a contextual image of where this is, and it'll be a Hubble image, and maybe we're missing something in the Hubble image, or we only have one filter of the Hubble image. We can use ground-based observatory data, and then we can use the high resolution like Hubble filter as that luminosity filter, and that can be very helpful. So there are definitely cases. It really depends on the story and what we're trying to say, because sometimes it can be a little confusing too if we're kind of swapping infrared with visible or vice versa. But definitely for Webb, or actually I should say definitely for Hubble, we can sometimes use ground-based observatories. And then for Spitzer, or I should say, I'm like answering my question. For Webb, we can sometimes use Spitzer data to fill it in.
Great. And Isaac is wondering about tool selection, and you obviously shown us some things in Photoshop, and he's wondering any reason that's chosen over PI, or maybe you can talk a little bit about what tools you select and why.
Yeah, no, it can depend on the object that I'm working with. Sometimes I just can't get the look that I want, or I'm having a hard time balancing an image where it doesn't feel like I'm properly calibrating it. And sometimes PixInsight is actually a great place to start because okay, I'm definitely removing gradients here. I'm definitely neutralizing the background. And sometimes it's really hard to do just with stretching and Fits Liberator. So it really is sort of a conversation with the data for me at which one is the best thing to work with. I know that Joe DePasquale, he tends to use PixInsight more heavily, and then I tend to use Photoshop more heavily, just because we're just more comfortable with those mainly. My background is in art and design, so I did work in Photoshop a lot, and it's more about what is easier to do, because a lot of these things can be sort of, quick turnover or quick, we have to get these out very quickly because it's like a very interesting discovery and it needs to be done quickly. So it's like, okay, how can we get this done?
So you grab what's familiar, right? Yeah.
Yeah, pretty much. But yeah, if we have the time, we like to explore the different things because, every tool has its pros and cons. And yeah, it really depends, I think.
Great. And I think the last question that we have out there is, where might we be able to find information about the processing pipeline?
Oh, yes, I will also send that here. I don't think I put it on the slide, unfortunately, but yes, I can share a link that has all the documentation, all the different stages, all of the code, and also there's webinars. So it actually goes through all the different stages and all the different observing modes too. So like spectra imaging for the different instruments. So I'm happy to share that. It's very useful.
Terrific. Getting a lot of compliments on the presentation and everyone seemed to really enjoy it. So thank you very much, Alyssa.
Awesome. Happy.
And are we all set?
Of course, as soon as I said that, one last question comes in. How long does it take from when the data is captured until it reaches you for post-processing? And then are you on a deadline to complete an image?
So yeah, so it depends sort of. And when it comes to like anniversary images, like the early release images that came out, it was pretty much like a 2-day turnover in terms of like 2 days from when the data was run through the pipeline and we received it from the telescope too. And that was like, hey, we really need to get this done. And then from that, it was usually like 2 days for us to finish processing from that point. And so it took a little bit longer to process it, or I should say post-processing it, because this is when the pipeline was still a little bit new. So there's a lot more artifacts that we had to deal with than normal. But generally that's about what it is in terms of timeline, but it also has to do with when we need something. Like if they say we need something tomorrow, then this is going to be done tomorrow. But if given the time, we'll play with it more because we really enjoy like exploring these images. So we'll try our best to represent it in like the best way. So we might try different ways just to see what works best.
Right. I think that's all the questions. Thank you so much.
So,
Yeah, great.
Alyssa, thank you so much. It's a great presentation. You held your audience and actually built it a little bit as time went on. This is posted on YouTube, so you can check in a week or so and see how many people view it. But I suspect we're going to have a fair number. This is going to build nicely. And if we're all set, I think it's time to say goodnight to our audience. So who's running the show tonight?
Me.
Okay.
Hi.
All right.
Good night, everyone. We'll see you next week. Another great presentation. Alyssa, thank you so much. If you want to hang with us a little bit for a few minutes after we close the show, you're welcome to do so.
All right. Good night, everybody.
Thank
Good
you,
night.
everyone.
Good night.